Okay, so we're doing section 8.3, testing the difference between means, and now we're going to do it for dependent samples. Okay, so up to this point, we've only dealt with independent samples. Now we're going to talk about dependent samples. So first, we're going to need to be able to calculate the difference D. Okay, the difference D is equal to the first sample data entry minus the data entry corresponding in the second sample. Okay, for each data pair. Then once we get all those differences D, we're going to find the average D bar. Okay, D bar is equal to the sum of all the differences divided by how many total pairs there are. It's the mean of differences between the paired data entries in dependent samples. Typically dependent is like before and then after data. Okay, before and after data. All right, so there's 4 things we got to satisfy. For one, we've got to have a random sample. Okay, random sample. Number 2, it's got to be dependent. So dependent sample. All right, number 3, the population are normally distributed. Or the number of n of pairs of data is at least 30. In pairs of data is at least 30. All right, so say I had, some sample like, I had like Bob, Sue, Sally, okay? That would be N1 here equal to 3. But then this is before the diet, and then after the diet I measure Bob, Sue, Sally. Okay, maybe that N2 is 3. The total people I have in my sample is just 3, N equal to 3. There are 3 pairs, 1, 2, 3 pairs. So that's how I calculate it. I don't say N equals 6 there. N is 3 because there's N pairs of data. Okay? Just want to make sure that was clear. If this is true, I have a sampling distribution for D bar that is approximately a T distribution. So the sampling distribution for D bar is approximately a T distribution with degrees of freedom equal to n minus 1. Okay? Test statistic, D bar is equal to the sum of the differences divided by n. The standardized test statistic is T equals D bar minus mu D over SD square root of n, where my degrees of freedom is found by n minus 1. Mu D is the hypothesized mean. Mu D is the hypothesized mean difference of paired data in the population. What do we always do? In the hoe, we assume there's no difference So if there's no difference, then this is going to end up being assumed to be 0. So this piece drops out. So really we just need to know how to get SD. SD is the square root of the sum of the differences minus the average of the differences squared over n minus 1. Right? This formula that we talked about way back when, early on in the semester, how to calculate the standard deviation. I don't ever want you to calculate the standard deviation by hand. If you were given a list of numbers, I want you to get that list of numbers, go to your calculator, see if I can do this. Go to your calculator. I may not be able to do it. Hit the stat button, hit edit, and then you can type in your numbers. Maybe my numbers like 1, 6, 5, 6, 69, 32. There we go. Okay? And then I want to hit stat, calc, 1var stat, frequency 1 time. Oh, let's try this again. Your calculator might be different. Stat, calc, 1var stat, enter. All right, and now I can see my output here, okay? So it tells me my average X bar is this 19.83. The X bar is your D bar. The SX is your SD that you want. So your calculator is going to do this for you. Don't do that by hand. Use your calculator. Okay, we don't want to do that by hand anymore. The standard deviation of the differences between paired data entries in the dependent sample. Okay, so let's run through an example here and I want to show you how this works. All right, so shoe company claims that you can increase vertical jump. Why would you want to increase your vertical jump? Maybe, you can touch the net right now on a basketball goal and you want to be able to dunk it. So you go out and you buy these magical shoes. It's going to fix all your problems, right? Okay. So 8 randomly selected people, they have their vertical jump measured before and after 8 weeks of training. Measured in inches, let alpha be 0.1. So 10% alpha. Is there enough evidence to support the manufacturer's claim that it actually makes the jumps, that they're claiming that their shoes are going to increase the jumps? Here's our before and our after data, and we need to calculate the differences. All right. So before we do this, we got to know, is it random sample? Yes, randomly selected. Dependent. How do we know it's dependent? Because it's the same people measured before and then after. Definitely that's dependent. N equal to 8. That is not greater than or equal to 30. So yes, good. Normally distributed. Jump heights are normally distributed. Normal distributed tells me that I can use the t-test. Okay? So I'm going to use my t-test here. All right, what's the claim? The claim, okay? The claim is athletes can increase their vertical jump heights. Now, how are we going to do this? Because we got to talk about mu d. What is mu d, right? Mu d is calculated by mu1 minus mu2. When I think of this, I think of it sequenced in time. Okay, sequenced in time. Before is my mu1, after is my mu2. Okay? Now, if my jump height is going to be increased, okay, so this is the hardest part of the test, I think, is figuring out what to call mu d. So increase the jump height. That's the claim. How do I write that in terms of mu d? So this is equal to the jump before minus the jump after. If I'm trying to increase my jump height through the training session with the shoes or whatever it is that's going to increase my vertical, I would want this number to be bigger. If this number is bigger than this one, and I'm subtracting that number, then this whole thing should be, my claim says it should be negative, okay? The claim says it should be negative. So what does that mean? That tells me that mu d is less than 0. That's the claim. If my jump height is going to increase. So personally to me, I think this is the hardest part, figuring out what the ha and the ho is. So the ha here, what about the ho? The ho is the opposite, the complement. That's mu d greater than or equal to. All right, what type of test is it? Well, it looks like it's pointing to the left, so it's a left-tailed t-test. Okay, left-tailed t-test. All right. Now, all we need to do at this point is figure out the differences. So I do, for the first difference, I'm going to do 24 minus 26, and that gets me -2. Then the next one I do 22 minus 25, and that gets me -3. And I keep running down, I get 0, -1, 2, -2, -5, -3. Looks like a lot of negatives there, so maybe the claim is true, right? So we need to run the statistical test to see if it's true or not. I'm going to show you how to do this by hand. D bar is the sum of the d's over n. What are my d's? It's -2 plus -3 plus 0 plus -1 plus 2 plus -2 plus -5 plus -3. And then I divide by n equal to how many differences did I have? I have 1, 2, 3, 4, 5, 6, 7, 8 pairs of data, so divide by 8. If I do this, I get -14 over 8, which gives me -1.75. So my d bar is 1.75. SD, if I calculate this, this is going to be the difference. All right, the first difference is -2. So -2 minus -1.75 squared plus the next one, -3 minus. Now, what are these? Minus and minuses turn into a plus. So I'm going to go ahead and make this plus for each one of these. Save us some time. Plus this squared. And then the next one, 0 plus 1.75 squared. Plus the next one, -1 plus 1.75 squared. I hope I didn't do that too fast. The reason I'm plussing and not subtracting here is because it's really d minus d bar. But what do we know d bar is? D bar is a -1.75. And so when you do that, negative and a negative make a positive. That's why I'm writing that plus, okay? And then I have 2 plus 1.75 squared, and then -2 plus 1.75 squared, plus -5 plus 1.75 squared, plus -3 plus 1.75 squared, all divided by 8 minus 1, which is 7. If I take the square root of all of this big nasty stuff, my answer is 2.1213. Okay, 2.1213. Now that is a lot of work, but we can definitely do it. And the t is equal to d bar minus mu d over sd, square root of n. D bar we found to be -1.75 minus, we assume 0 in the ho. Okay, the null hypothesis, assume there's no difference. Standard deviation, 2.1213, divided by square root of n. square root of n, square root of 8. And when I type this in, let's see, looks like I get negative 2.333, something like that. And so when I do my t-test, okay, I know it's a left-tailed, so I know I'm going to be on this side for my critical value, so it's a negative, zero's in the middle. Alpha is 0.10. It's a one-tail alpha, and the degrees of freedom is n minus 1, so n minus 1 is 7. So I go look up my t-table, degrees of freedom 7, so that gets me alpha 0.10, so 1.415. 1.415. What did I do wrong there? Well, it's not positive, it's a left-tailed test, it's negative 1.415, so make sure to make your negative there. Okay, so if I'm in this region, the shaded region over here, I reject. Where is this going to fall? I find that my t value, my test statistic, the standardized test statistic, is going to be in the rejection region. Therefore, I reject H naught, reject the hoe, since 1, t is less than negative 1.415, so I reject. And what does this tell me? It says there is, why do I say there is? Because I have reject. There is enough information, enough evidence at alpha equal to 0.10, so that's a 10% level of significance, to, now do I support or reject? Okay, my claim is the ha, so I'm going to support. Only thing I do with the hoe is reject. So support, okay, support the shoe company's claim that you can increase vertical jump heights using their shoes. Okay, this would be very powerful marketing for a company to be like, hey, look, statistically, if you use our product, you will increase your vertical jump height. This could be very, very powerful. Okay, very powerful marketing to be able to say, look, if you use our product, it's going to make you be able to jump higher. Now, does it say how much higher? No. That goes into a different type of question. Instead of saying, there is a difference, you would have to say maybe that difference is 10-inch difference. And if that was the case, this would no longer be 0. That would need to change to be like 10. Okay, so that's how the test changes when you put some figure to how much greater you want it to be. Right now, all we're saying is, we're just claiming that there's a difference or no difference. Okay, and that's why we assume mu d is equal to 0. But if you wanted to show like some amount of difference greater, then you would use whatever number you wanted to use in that point right there. So let me show you how you would do this in your calculator. What you would do is you would take the differences, so you're going to have to calculate the differences. There's no way around it. So you've got to calculate the differences. You type those differences into L1, okay? So I'm going to have a column with just these differences right here. All right, so let's see if we can do this. See if we can get the same answer. So let me go back in here, and I'm going to go to Stat, Edit, And now right now I've got a whole bunch of numbers in my L1. So what I'm going to do is I'm going to hit the delete button until they're all gone. And now I'm going to enter in my differences. -2, enter. -3, 0. Okay, 0. -1, 2, -2, -5, and -3. All right, so I've got them all entered in. Now what am I going to do? I'm going to hit, let's see here. Let's go to stat. And then I wonder if we get no tests are available. Okay, so if I did this, I could run it. With mine, what you would do, you go to test and then go to the t-test. And then it's going to ask you input data or statistics. You're going to use data and you're going to put L1 for your list. And it's going to be a left-tailed test, so less than mu naught or mu ho, right? And then hit the calculate button. But since I don't have that on my cheat calculator, the free app I have, then I'm just using this here. And I hit enter. And this gets me those same values. I hope that looks familiar. The X bar is your D bar. The SX is your SD. Okay? So that tells you, you don't have to do the math on that. You can just use your calculator as long as you know X bar is D bar and SX is the SD. Okay? So just to write this down for you, your TI-84, you could do calculate the D column by hand. Okay, so you'll have to do that by hand. Then type into L1. And then to do that, just hit stat edit. Okay, no big deal. That one's pretty easy. And then once you do that, hit stat test t-test. Okay? And under the t-test, you're going to have input. And you're going to select data. Okay? Because you have a list of numbers. Anytime you have a list of numbers as data, if you have the X bar, SD, all that stuff, you can use statistics. Your mu-d is going to be 0, like we talked about. The list, what list are you getting it from? L1 if you typed it in your L1 list. Frequency, how many times you want to count it? Just once. Or leave it blank, either way. And then the type of test, you can either have two-tailed test, you can have left-tailed test, or you can have right-tailed test. Ours was a left-tailed test. I select this one, and then I hit the calculate button. So I hit calculate, and what does it output? The output is mu less than 0. That's my ha. Okay. T equals -2.333. That's what we got earlier, right? We got that right there. Okay. P equals 0.026178. So X bar equals -1.75. SX equals 2.1213. N equal 8. Guess what? SX is SD. X bar is D bar. Okay, so something to make sure that you know. These things right here represent those things there. So looks like everything is exactly how we got it earlier. Okay, a p-value of 2%, little over 2%, almost 3%. This is a p-value that's less than alpha that was what did we say alpha was for this test? We said alpha was 10%, right? So 0.1. If you have a small p, reject the ho. H naught reject. And we came up with the same conclusion, didn't we? All right, so looks like everything worked out for us. Okay, guys, Good luck working those problems from 8.3.